So did you try? Any answers that you people are getting? See, it's a formula based question only. It says what a 10 ohm resistance coil has 1000 turns. So number of turns are given to you as 1000. Now initial flux is given to you as 5.5 into 10 to the power minus 4 Webers. This was the initial flux. Now the flux has decreased and decreased to what value? 0.5 into 10 to the power minus 4, this much value. Okay, EMF you have got as 50 volts. All right, let's see. So this is what this is. It should be 50. Okay, let's see. Time period is given to you as 0.1 second. So let's just write down everything that we have. Resistance is 10 ohm. Initial flux is given to you as 5.5 into 10 to the power minus 4 Webers. Final flux is given to you as 0.5 into 10 to the power minus 4 Webers. Because initially it was 5.5 into 10 to the power minus 4. Now it has decreased to 0.5 into 10 to the power minus 4. In this time period, that is given 0.1 seconds. Now we have to find out the EMF and the charge flow. So we have the formula for it. If we know the time period, time we know, time duration we know, 0.1 seconds. So EMF is what? EMF is rate of change of flux. So EMF, formula of EMF, this is minus d phi over dt. Delta phi will be what? Initial minus final we cannot take. Phi 1 minus phi 2 we cannot take it. We have to take final minus initial. So 0.5 minus 5.5. This term. 0.5 into 10 to the power minus 4 minus 5.5 into 10 to the power minus 4. This much Webers. So this is how much? This will be this will be 5. 5 into 10 to the power minus 4. This much Webers. Fine, so we have delta phi with us. Let's just put it. Okay, this will be minus 5 into 10 to the power minus 4. Now, this is a negative sign. Already a negative sign is present. This is minus 5 into 10 to the power minus 4. And dt, this is 0.1. No? So we can write it as 10 to the power minus 1. So this becomes what? Minus minus, this becomes plus. This can be written as what? This can be written as 5 into 10 to the power minus 3, this much volts. Clear? Regarding the second part, one more thing is asked in the question to calculate the charge. So charge formula, we had done it separately. This formula. dq is equal to minus d phi over dr. So minus d phi you already know. Resistance, you just have to divide it by 10. So delta phi was what? dq will be delta phi. That is 0.5 into 10 to the power minus 4 minus with a negative sign. 5.5 into 10 to the power minus 4, this much, divided by resistance is just 10. So this was already minus 5 into 10 to the power minus 4, no, by 10. So this becomes plus, this is 5 into 10 to the power minus 5. Fine, like this only. In the formula, you had to put these values. Now, this was a formula based question, but we'll do some questions. Some more questions we'll do that will just directly relate with phi. So first, note down the solution. Then we'll do one more question before moving on to Lenz law. One more thing. This was also given. No, number of turns is also mentioned. 1,000 turns are also mentioned. No, so this I have calculated for a single turn. You have to multiply it with 1,000 also. So for this is for a single turn. So for n number of turns, this will be 5 into 10 to the power minus 3 into 10 to the power 3. That gives 5 volts. So did you try the question? Any answers by anyone? See what is meant by the question. It says what a coil of cross-sectional area A lies in a uniform magnetic field, which is B, with its plane perpendicular to the field. Atif answer is right. Correct answer. This is the answer for the first part. Something is missing in your answer. Just check it again. This should be the answer for the second part. Now, in this position, normal to the coil makes an angle of 0 degree with the field. The coil rotates at a uniform rate to complete one rotation, not on rotation. This is one rotation. To complete one rotation in time t. Now, you have to find out the average induced EMF in the coil during the time interval when the coil rotates from 0 degree to 90 degree and 90 degree to 180 degree. Now, what is meant by the question first? Coil is there, cross-sectional area A is there, uniform magnetic field B is there. Till here it's clear. Now, it says in this position, normal to the field makes an angle of 0 degree. What do we call? Can anyone tell me what do we call this normal to the field? We have a special name for this quantity. See, it's like if this is the coil. What do we call this? This normal to the coil that it makes.
Area vector.
Area vector. Yes, right. It's known as the area vector. So this is the area vector. So perpendicular to the coil makes an angle of 0 degree with the magnetic field. It means magnetic field is like this. Here, this was the question. Now it says, let's say this is the coil. So this is the initial position of the coil. When the coil completes one rotation like this, then the time period becomes T. That was given in the question. And at the end, what did the question ask? You have to find out the induced EMF when it rotates from 0 degree to 90 degree position. From 0 degree to 90 degree. See, phi 1 will be what? Initial phi will be what? 0 degree. Theta is 0. Theta initial is 0 degree. So what's the normal formula of magnetic flux? Hamza? Normal formula, what's the general formula of magnetic flux? Yes, Hamza? Magnetic flux, we did it in the last class. BA cos theta. Yes, BA cos theta. B dot A also you can say. Fine. So good. So according to this formula, BA cos theta, if you put B is the magnetic field, A is the area. Cos theta means cos 0 degree. So cos 0 degree is 1. Initial phi will be BA. Final angle is given to us what? Final angle is 90 degree. So phi final will be BA cos 90 degree, which will be 0. Fine, till here it's clear. Now EMF is what? Minus delta phi divided by delta t. So delta phi will be what? Again, Kulsum, same thing I think that has been done by Atif. Magnitude is right, something else is missing. Just see. So EMF is what? Minus delta phi divided by delta t. Now change in flux. Final flux is this. Initial flux is what? Initial flux is PA. Now it's correct. So EMF will be, this will become, this is minus, final is 0, minus BA. We have divided by delta t. Kulsum, what was the time that you took? Kulsum, what was the time period that you had taken? Reason? Just give me the reason. Just explain it. You're right. That's correct. Why did we choose this time period? C class. Why did we, how we have to choose the time period? See, this is the starting position. So from here it went then it went here, then it went here, then it went here. This was the rotation of the clock, which gave us the time period t. So this was what? This was 0 degrees position. If you rotate it from 0 to 90 degree, see how much amount of time has been swept by it. 0 to 90 degree. If we divide this whole time period in 4 parts, this becomes what? 1 by 4, 2 by 4, 3 by 4, 4 by 4, complete time period. So from 0 degrees to 90 degree, this is how much time? 1/4 of the whole total time period, no? So time period will be what? Time period will be t by 4. So this becomes t by 4. This is t by 4 only. Now, if you write it completely, this becomes what? This becomes plus, minus, minus. Okay. No. Your answer was right initially. See, this is the final flux. No, 0 minus minus B. So this will be 4BA divided by T. Final flux is what? Final flux is 90 degree. So if you subtract it, you will get it as T by 4. Final flux is 0. So your initial flux will be what? This will be plus 4BA by T. That is right. Now here see what will happen. In this final flux was 0 degrees. Here, this was your final flux. 0 is final flux is 0. Initial flux is what? Initial flux is BA. So you're subtracting final minus initial. That will automatically give you minus B. So minus minus combined with this will give you plus 4B only. So your answer was right initially. Kulso Manatif, it will be plus 4BA by T only. Now in the second part, let's see. Now in the second part, it's from 90 degrees to 180 degrees. So initial position will not be this time. This was 0 degrees. Now initial position will be what? Initial position will be this. This is now 90 degree position. So from 90 degree to 180 degrees. This is the case. So again, how much time has been spent? Can anyone tell me the time period for this time? From 90 degree to 180 degrees. What will be the time period? It will be T by 4. Yes, it will be T by 4 only. Because again, if you divide it into 4 parts. So this will be one part, this will be second part, this will be third part, this will be fourth part. Out of which we have covered this part only from 90 degree to 180 degree. So time period will be T by 4 only. Difference will come in our calculation. See, theta 1 this time, initial theta 1 that we have started with. This is 90 degrees. So initial flux is now 0. And final theta is what? Theta final is this was given 180 degrees, no? So final will become what? See, this will be BA cos 180 degrees. So BA cos 180 degree means minus B. So now if you write the values, and time period will be T by 4. So if you write the values of EMF, this will be minus final minus initial, which you write it as minus BA divided by time period is what? Time period is T by 4. This comes out to be 4BA divided by T. So this is from which time? This is from 90 degrees to 180 degrees. Now, if I shift the time period, let's say, Krishna, you tell me, if I had started from 0 degrees and the coil had completed till 180 degrees, what would have the time period that I would have chosen? Time period.
T by 2.
T by 2. Got it? Hamza, you tell me. If it starts from 90 degree and it covers 360 degree, then how much time period? 90 degree to 360 degree. Just divide 360 degree into 4 quarters, 90, 90, 90, 90 each. T by 4 from 90, if it will start. Sarah, can you answer? 90 degrees to 360 degrees. T by 3. Now it's right. It will be T by 3. T by, not T by 3, Hamza, this answer. Sarah, you're right. 3T by 4. That's right. We are, see, just divide the time period into 4 parts, not like this. The way we have fractions, no, in our lower classes, like this. Divide the time period into 4 parts. This is 0 degree, this is 90 degree, this is 180 degree, this becomes your 270 degrees. Fine, like this. Now, out of this, if you take 3 parts, so that becomes 3t out of what? 4. So that is 3t by 4. So yes, Sarah, your answer is right. I hope you've got it. Hiba, you tell me. If we start from 180 degrees to 270 degrees, what should be the time period that we should choose? Hiba. From 180 degrees to 270 degrees. (180 degrees) is the initial position of the coil. T. See, Hiba, if I start from here and I reach here, how much fraction is this? If total fraction is T, how much fraction is this? If total is T, the portion that I have shaded, T by 3. See, how much is the total? First, tell me, how many these divisions are you able to see? 4 or 3? 4. So out of which I have taken only 1. So that becomes T by 4. See, total is T. You have divided it into 4 equal parts. So if you just take one part of it, this is just one part of it, no? That becomes T by 4. Clear, Hiba? Like this you have to consider. All right, Kulsum, you tell me, if it starts from 90 degree and the coil stops at 270 degrees, what will be the time period that you will choose? Yes, Kulsum, if you start from 90 degrees and you reach at 270 degrees, then what will be the time period that you will choose? Kulsum? No idea, Kulsum. Sneha, can you try? If you start from 90 degrees and reach to 70 degrees, final position, what will be the time period that you choose? Sneha? Atif?
T by 2.
T by 2. See, from 90 degrees, if you're going to 270 degrees, it's like starting position is this 1, 2. So this becomes what? Total time fraction that you have chosen is the half of it. So T by 2. Is it clear to others, Kulsum and Sneha? Now clear to both of you how to choose the time period if a coil is mentioned? Fine, because in the questions that are there, no, different values are there, out of which I have only taken two, 0 to 90 and 90 to 180 degrees. Different positions are given, 180 to 270, 272 back to 360 like this. So I think you will be able to now choose the time period. So just note it down. Then we'll start with Lenz law. Akif, I wanted to ask you regarding the video lectures. The last topic, the last class that you had attended before attending the last one. Did you attend the chapter 5th that we did? Earth magnetism is left there, but apart from Earth magnetism, we have completed certain topics of chapter 5th as well. So tell me if you've how much portion did you already completed? So I'll send you the video lectures. Now the next topic that was left is Lenz law. Now Lenz law, from the Lenz law, you will get to know why we had to put that negative sign. Now Lenz law states what? Lenz law says that induced current is there and there's a certain specific direction of this induced current. So this direction of induced current is in such a way that its aim is to oppose the cause that is producing it. Means what is meant by the statement? Induced current is generated by what? Change in magnetic flux that we had seen in the last class. Whenever magnetic flux changed, and induced EMF as well as induced current was generated. So induced current is caused by what? This induced current the cause of this induced current is what? The change in magnetic flux, delta phi. That's what we had been seeing, and that's the formula that we have been using. Now Lenz law says that whatever is the changing flux, no, let's say it's decreasing, so induced current will try to increase the flux. Whatever is occurring to the magnetic flux, whatever change is occurring in the magnetic flux, induced current will develop its direction in such a way that it will oppose it. Lenz law means only to oppose the cause that it's producing you. So induced EMF, what's the cause of induced EMF? The cause of induced EMF is the rate of change of magnetic flux. So induced current develops such a direction which opposes the cause that it produces it. And what's the cause that produces itself? It's the rate of change of magnetic flux. First, let me write down the statement. It says that direction of induced current, and the question in the exam also, the questions come, write the direction of induced current, write the direction of induced magnetic field because of the induced current. So induced current is very important to understand over here. Direction of induced current is such that there's a direction of induced current, it's such that it opposes the cause that produces it. Now, what is this cause that produces it? It's the rate of change of flux. So the cause that produces it, it's the change in flux. So this is what is meant by Lenz law. Lenz law simply says that the basic definition or the law, Lenz law, is that only direction of induced current is in such a way that it will try to oppose the cause that it is producing it. Now, what is producing the induced current? The change in flux. So it will somehow try to oppose it. Now, how will it oppose it? You will see. One more thing, Lenz law, this also comes a statement, Lenz law is in accordance with what type? So Lenz law is in accordance with law of conservation of energy. So Lenz law is in accordance because work is done there. Work is done to overcome the force of attraction. Work is done to overcome the force of repulsion. So that's why because of the work done, we have Lenz law, which is in accordance with law of conservation of energy. So it's in accordance with law of conservation of energy. That's why in this formula, no, minus d phi over dt, we had this negative sign. This was because of Lenz law only. This means what? It means the direction of induced EMF. This direction of this is to oppose this. That's why we had this negative sign. What's the direction of induced EMF? It's the direction which is in opposition to this. That's why we had this negative sign. But it does not get clear by just the statement. See, let's see some more examples. A very quick revision of what we have already done. Then only you'll be able to understand certain things. If south polarity is developed, to check the direction of current, just write S Put the arrows, go along with the arrow. That will give you the direction of current. Just a second. Yes, now for the north polarity, I have told you just develop and draw this kind of end. Now go along with the arrows. That gives you direction of current. This we had done. One more thing we had done, right hand thumb rule we had seen. Why am I revising these? Because this will be used in Lenz law. Let's say direction of current is this. So what will be the direction of magnetic field? Or if direction of magnetic field is given, what will be the direction of current? So that's simple. Just curl your fingers along the sense of current. If this is the direction, this is the curling of fingers. So I have to curl my fingers like this. Thumbs gives the direction of magnetic field, induced magnetic field. So this is the direction of thumb, which is into the page. So clockwise current is giving me inwards magnetic field. This magnetic field, this is inwards. Similarly, had I known this magnetic field before, I didn't know the direction of current, I would have kept my thumb like this, then I would have seen the curvature of my finger. That would have been clockwise. So with the help of magnetic field, I would have received the direction of the current. Fine. Now coming to Lenz law. This was just a revision that will be used now. Now, what types of question come in the exam? And also to understand Lenz law. Let's say a coil is there, a circular coil is there, and a bar magnet is there. Fine, a circular coil is there and a bar magnet is there. Bar magnet has the polarity, north pole is there, let's say this end is south pole, and this is moving towards it. So what's the cause right now? The cause is the approaching bar magnet. I'll write down this as well. The cause is approaching bar magnet. With which polarity? North pole. Fine. According to Lenz law, induced current will develop in such a way that it will oppose the direction that it produces it. So what's the polarity right now? The polarity is north pole. I just have to find a way by which north pole could move away. If north pole is moving towards the left, induced current's work is to move this magnet towards the right. Just oppose this. If it is coming upwards, going upwards, move it downwards. If it's going left, move it right. Just opposite action. So if north pole is coming towards the magnet, induced current because of Lenz law will try to do what? Make it move away from the coil. If this is the coil, magnet is approaching. Coils, the induced current work will be to develop in such a way that it opposes it and the magnet goes away. Now, what polarity should be there in the coil so that north will go away?
North pole.
North polarity, right, Krishna? See, if north pole is developed somehow in this, north pole is developed. So what will happen if north pole is developed? So north will repel each other and this magnet will move away. So opposition has been done to the cause, and the direction of induced EMF will be anti-clockwise. This is one type of question that comes. Let's see some other examples. Same bar magnet is there. Let's say this time south polarity and this is north polarity. Fine, south polarity is there and north polarity is there. This time south polarity is approaching. So what should be the polarity on this coil?
South polarity.
South polarity, exactly. Good answer. It will be south pole. Why south pole? See, now the cause is what? South pole is coming. Induced current will try to move it away. Just its work is right now to move this south polarity away. And the best and the only way to move by generating a same polarity. So the best way to move the south polarity is by generating the south polarity in itself. This was the work that was done by the coil. So it developed south polarity, and again, this will be the direction of induced current. So this is clockwise. So these kinds of questions are asked in the exam, that if south polarity is approaching towards a coil, circular coil, what is the direction of current developed, induced current developed? So induced current develops in clockwise manner, so that the polarity is south, and south repels south, because repulsion is the only solution now. Let's take some more examples. This is a coil. North polarity is there, south polarity is over here. The coil is moving away right now. So can anyone tell me what should be the polarity that has to be developed in the coil?
South polarity.
South polarity. Reason, Krishna?
It should be opposite to the direction.
Opposite to the direction. Just explain why south polarity.
It should oppose the cause of the product
Which
that
is
it produces.
that it produces it. Now North Pole is moving away. Right? North Pole right now it is moving away. What has to be done just to move it back to the coil? Earlier, magnets were moving towards the coil. Right now, what is happening? Magnet is moving away from the coil. So if magnet is moving away from the coil, induced current will try to do what? It will try that magnet does not move away. Magnet should come back to the coil. So attracting North Pole is the aim now. And how can North Pole be attracted? North Pole can only be attracted by developing a south polarity. Got it? Krishna, you were saying this only? Is it clear?
Yes, ma'am.
Okay. This is South Pole, this is North Pole, this is moving in this direction. All of you write me in the chat box what should be the polarity developed by the coil. All of you right, not polarity. Why? What is happening? South polarity is moving away. How can we oppose it? By developing north polarity. North polarity will only attract it. If we develop south polarity, the magnet will move further away. So north polarity will only attract it. So this develops what? This develops north polarity. Direction of induced current will be anti-clockwise. Clear till here? Like this. So first note it down till here. We'll see one more case how questions come. Now class, one more type of coil and the magnetic field problem that comes in the exam. One is this, these kinds of question come and it is a state Lenz law. Why is it in conservation of energy? So reason is that only because work is done to overcome this force of attraction or force of repulsion according to the cases. So that's why you have to write all these things. Now this second type of question that comes is, let's say magnetic field is there. This is a space where magnetic field lines are kept. Now a coil is there. Let's say this coil is there. This is your first coil. Coil number 1 is this. This is a rectangular random coil that I have drawn. Now let's say coil is going upwards, moving away. For example, let's say. So Krishna, you tell me, is the magnetic flux increasing or decreasing? Krishna,
Decreasing.
decreasing. Reason? What is magnetic flux? Krishna, magnetic flux. See, you are right. Your answer is right. It is decreasing. Reason? I'm just asking the reason.
Ma'am, since it's moving away,
See, number of magnetic field lines crossing area normally is known as magnetic flux. Fine. So here what is happening? You are right. It is moving away. So what is happening? It is moving away. So number of magnetic field lines that are enclosed within this, it is decreasing. So that's why the magnetic flux is decreasing. Clear, Krishna?
yes, ma'am.
Like this only. So what happened? Now the magnetic flux is decreasing. So aim of induced current. Right now what is happening? Magnetic flux. This is decreasing because magnetic field lines are decreasing. So work of induced current will be, the aim of the induced current will be to increase the magnetic flux. Induced current will try to increase magnetic flux. It will try, induced current will try to increase the magnetic flux. This is the aim. So increasing the magnetic flux means what? Increasing the magnetic field. If magnetic field gets increased, then magnetic flux could be increased. Now understand this carefully because in the next two parts or something else, I'll ask you people one by one. So listen and understand this carefully. This is very easy. A very scoring topic is there in your Lenz law. So induced current try to do what? Induced current tries to increase the magnetic flux. Now, what is happening? How will it increase the magnetic flux? By increasing the magnetic field. So if magnetic field is pointing into the page, inwards, if something is magnetic field is moving into the page, see, like this. Let's say 5 magnetic field lines are moving into the page. Just a second, just yes, so let's say 5 magnetic fields are moving into the page. 5 magnetic fields are into the page. If I have 4 magnetic fields with me and I bring them in the same direction, so what will be the net magnetic field? It will be 5 plus 4, which is 9. Now magnetic field number has increased. If I have those magnetic field lines as 5 and I bring the other 4 magnetic fields in opposite direction, what will happen? Net magnetic field will be 5 minus 4. That is only a single magnetic field. Now, what is the work of induced current? Induced current wants to increase the magnetic field. So it will prefer this pathway. It won't prefer this. It means it will try to bring the magnetic field in such a way that the net magnetic field increases. Then only this net flux will increase. So right now, magnetic induced current will try to do what? Induced current will try to develop the direction of magnetic field in such a way that there is net increase in magnetic field. Then only the cause will get opposed by it. So what will happen right now? The aim is to increase it. Now, if I have to increase the magnetic field lines are pointing into the page. If I want to increase the magnetic field lines, I will try that magnetic field lines are into the page. So I have kept my thumb like this. Now, what's the curvature of finger? It's clockwise. So it means this is the direction of induced current, because induced magnetic field is also inwards to increases. Now the opposition has been done. Is this clear to all of you? First tell me. Yes, no, what?
Yes, ma'am.
Ma'am, can you repeat it once more?
See, magnetic flux was decreasing, as rightly answered by you only, because it was decreasing since amount of magnetic field lines that were enclosing by it, they were getting decreased like this. Now, aim of induced current is what? Is to increase the magnetic flux. Somehow it has to develop such a direction that net magnetic field should increase. Magnetic flux has to increase. So decreasing magnetic flux, forget. Your aim is now to increase magnetic flux. So if I have to increase magnetic flux, if I have to increase magnetic field, so I will want that all the magnetic field, induced magnetic field and the original magnetic field, both, if they are pointing in the same direction, they will get added. If they are pointing in opposite direction, they will get subtracted, and it will reduce the net magnetic field. Right now I want magnetic field to increase. So if I take the direction of induced magnetic field also inwards, and original magnetic field is already inwards, what happens to the net magnetic field? Both the magnetic field gets added and it becomes a greater number. So it means now the opposition has been done. So we have chosen a direction of induced magnetic field. What should be the direction of induced magnetic field? Inwards. Is it clear till here, Krishna?
Yes, ma'am.
Now see, direction of induced current will be what? Direction of induced magnetic field is inwards. See curvature of fingers. Curvature of fingers are clockwise. Let's say you knew the current. If current is clockwise, how do you get the direction? So just opposite to it. Keep your thumb in the direction of magnetic field. Curvature of fingers will give you the motion of sense of current. So if thumb is inwards, then this becomes the direction of induced current. Now clear?
Yes, ma'am.
Let's take one more example. This is coil 2, let's say. This is moving here, like this. This is the pathway. Akifa, can you tell me, is the magnetic flux increasing or magnetic flux decreasing? Akifa, by looking at this figure. Akifa, are you there in the class? So in the last part, I didn't write something. No, induced current will try to increase the flux. Okay, Akifa, you're there. Fine. So what happened? Direction of induced current is in such a way to increase magnetic field. All right, Akifa, just look at this figure. Do you think magnetic field lines, if this coil is moving inwards like this, is the amount of field lines getting into this coil increasing, or amount of magnetic field lines that are getting enclosed within this coil decreasing? Increasing, decreasing? At least you can answer this much. It's increasing, definitely. So if it's increasing, it means magnetic flux is increasing. So in the second case, what is happening? Your flux is increasing. Here the flux is increasing. Atif, can you tell me what is the aim of the induced current right now?
To decrease the magnetic.
Exactly. Now, induced current will try to decrease flux. Fine. Now, it will try to decrease the flux. Hamza, you tell me, should the induced magnetic field point outwards or inwards? The induced magnetic field. This is the original magnetic field that is going into the page. What should be the direction of the induced magnetic field? Again into the page, yeah, out of the page. It has to be outwards. Perfect, Hamza. Reason? Because if this moves outwards, then only net magnetic field will be less. Otherwise, if it is inwards, then net magnetic field will increase like the previous case. We don't want to increase it now. We want to decrease it this time. So, the induced magnetic field will point outwards. The induced magnetic field, it will try to point outwards. Sarah, can you answer what should be the direction of induced current? If the magnetic field has to point outwards, what should be the direction of induced current? Sarah, it will be anti-clockwise, yes. If see, magnetic field, induced magnetic field is outwards. My thumb is here, like this. So this is what? This is anti-clockwise. Like this is anti-clockwise. And here direction of induced current, this was. Did you get it? This way you have to solve questions, and these types of questions are given in your NCRT also. A, B, C, D random loop shape is there, and if it is increasing, exiting from one corner, entering into other corner, like these questions, and they come in the exam, and they are easy like this only. So did you get it? Anyone has any doubts in this? Because Lenz law is only theoretical. You don't have any numerical. This is all about Lenz law. I have ended it. You don't have any numerical. Lenz law will be asked, the statement will be asked, and these kinds of examples are given. This kind of example is given. Tell me, any doubts still here? Do one thing, note this. Let's take a break of 5 to 6 minutes. Revise it. Any doubts, ask me. After 5 minutes, we'll then start with the motional EMF, which is the last topic for today. Note it down. I just want you people to be here after 5 to 6 minutes. Then we'll discuss it. Yes, class, everyone is here now. Let's start motional EMF. So yes, Lenz law clear to all of you. So I'm starting with motional EMF. So how questions in motional EMF come? Motional EMF questions are direct, very direct, and this is an easy topic. Motional EMF. One of the major topics that is left and is difficult, that can be induction. Motional EMF is very easy. The formula is easy. Just it gets keep on relating to the potential and the current electricity that you have studied. So questions come like, what is motional EMF? Reduce expression for EMF induced across the ends of conductor, and all these things. So both of these we'll do. Now, what is motional EMF? One, we had seen EMF in current electricity. Secondly, we had seen induced EMF here in this lesson only. That came because of rate of change of flux. Motional EMF is the induced EMF only, but it occurs at the ends of a conductor because when the conductor is in motion. So that's why the name motional EMF is given. I'll write down the definition. Motional EMF is what? It's the EMF induced across the ends of a conductor due to its motion. Due to its motion is important. That's why we call it, because of the name motion, we call it as motional EMF. In a magnetic field. In a magnetic field, it's called motional EMF. This is motional EMF definition. Now, how to derive it? Derivation is also very easy. See, we have considered like a rail, we have considered a U shape. Rail means track. So U-shaped rails are there. U-shaped rail means if I put a conductor, no, so it can slide away on it. Let's say I have this conductor, PQ conductor is here. So this can move on it. So that's why I'm saying these are what? These are U-shaped conducting rails. Now magnetic field lines will be inwards, perpendicularly to this. It's this PQ is a conductor that can slide over. It can slide over. So this conductor is what? This is this conductor PQ. This is moving with what? This is moving with V velocity towards the left, like this. It is moving with V velocity. Let's say the length of the conductor is L. Let's name this also PQ. So let's say this is R, this is N. So L is what? L is the length of the conductor. V is the velocity of the conductor P. Fine. So V is the velocity with which it is moving. So what will happen as the conductor slides towards the left, the area of the rectangular loop PQR is this decreases. And this decrease in the magnetic flux, because magnetic field lines are decreasing, so what will happen? Associated magnetic flux will also decrease. So if the magnetic flux gets decreased, we'll have induced EMF. And since it is coming because of the motion of this conductor, we call it as what? We call it as the motional EMF. So V is the velocity of it. Now, let's say suppose X is this length of the conductor, or of not the conductor, basically of the loop inside the magnetic field. X is what? X is the length of the loop inside magnetic field. So see, initially in the class, Hamza answered that flux was what? Flux was BA, magnetic field into area. So if you look over here, can anyone tell what is the area of this rectangular loop enclosed in this magnetic flux? Area of this loop. Area of a rectangle, simple area of a rectangle. This is the length. This is
Lx.
the width. Yes, Lx. So it will be L into X. So magnetic flux will be what? This will be B into L into X. Now EMF is what? EMF is minus d phi over dt. Let's put the value of phi. So EMF becomes minus dBlx over dt. BL are constant, so this becomes minus BL dx over dt. Dx over dt. Can anyone answer from the class? What is dx over dt?
Velocity.
Velocity.
Velocity. Perfect. So this is velocity. Now we are writing not only dx over dt, we are writing velocity as minus dx over dt. So the formula of the formula of EMF becomes what? BLV. Now, why did we write it as minus dx over dt, not as dx over dt? Here we wrote it as minus dx over dt because velocity v is in the decreasing direction of x. No, just look at the figure. Velocity is towards the left. If the velocity is pointing towards the left, as velocity is moving here, this x is decreasing. Had the velocity been moving over the other side, velocity would have increased. So both are in opposite direction. Velocity is in the direction where displacement is less. The x value is less. That's why we had to add this negative sign. I'll write down this as well. Velocity is in the decreasing direction of x. That's why I had to write this. Now, one more thing, one more small derivation is there, sort of derivation. It comes in the exam to prove this value of motional EMF using Lorentz force. So does anyone remember the formula of magnetic Lorentz force? Anyone from the class? Magnetic force, formula of magnetic force. We did. Nobody remembers from the class. Magnetic Lorentz force, we did. Let's say the conductor that is there, which is sliding over this U-shaped conducting rail, it has electrons present in it. So electrons are charged particles. So electrons will experience magnetic Lorentz force. What will be the magnitude of it? You people even had your test today. Remember? The test will be conducted on Thursday, the derivation test. You people are forgetting at such a fast rate now. Magnetic Lorentz force, QVB. So this magnetic Lorentz force will be equal to the electric force. Both of these will balance each other. So QVB will be equal to Q into B. QQ gets cancelled, and this relation is important from your EM waves also. This formula is used a lot in EM waves, VB into E, this formula. But right now, we are not concerned with this. Electric field was minus dV by dr. At least you people must be remembering this, minus dV by dr. So electric field will be potential by the length of the conductor. So here, if you put potential as E into L, so potential will be what? Value of E is VB and L. So potential or EMF, this is equal to BLV again. This comes in very short markers. If it is asked to prove using magnetic Lorentz force, then you have to prove it like this. Some more modifications that can come from here is this, that you have the value of EMF now. So if current is asked, certain formulas, if current is asked, so it will be EMF divided by resistance. So that will be BLV divided by R. Or let's say force. If we talk about force, force was BIL. Remember B, I cross L, BIL sine theta. So if it is asked, just put the value of current from here, BLB divided by R L. This is BIL. So formula becomes what? B square L square B divided by R. That's the formula of force. And last modification can be power. If power is force into velocity, what is force is B square L square V divided by R. This is force into velocity. So power becomes B square L square V square divided by R. These three formulas you should remember. Maximum it can go up to this. Maximum. Otherwise, questions from Motional EMF are direct. We'll also see a question right now, but before that, note it till here. If any doubts you people are having, just ask me. And please keep on revising the previous portions, like these formulas and everything. I hope you people are done with the derivations, because on Thursday I will for sure take the test from all the first 4 chapters. See, this question says that an aircraft with a wingspan of 40 meter. So this means what? Wingspan of 40 meters. It means the length, because here the length of the, instead of the conductor, you will have the length of wing of the aircraft. So length becomes 40 meters. Flies with a speed of 1080 kilometer per hour. So we have to convert it into meter per second. So this will come out to be 300, I think. Anyone just cross check, please, if it's 3 meter per second or not. So this comes out to be 300 meter per second. In the eastward direction at a constant altitude in the northern hemisphere, where the vertical component of the magnetic field is 1.75 into 10 to the power minus 5. Means vertical component of Earth's magnetic field. This topic is left from 5th chapter. This is 1.75 into 10 to the power minus 5 Tesla. You have to find out the EMF. So EMF will be what? It will be magnetic field into length into velocity, BLV. This will be 1.75 into 10 to the power minus 5. This will be 40. This will be 300. So this will come out to be around 0.21. So EMF will be 0.2. This is a question from your NCRT. So like this only questions come from Motional EMF. Just note down this. And when you people have completed the writing part, just text me done in the chat box. And be prepared with the derivations test on Thursday. I'll conduct the test within the class hours only. All right, so most of you have completed it now. So all those who have completed, you can leave the meeting, just join the class on Thursday. Induction is left and eddy current is left from this lesson. And we are almost towards the end of this lesson, and be prepared with the derivation test, and don't get absent. Derivations are from the derivation that we have discussed in the class. All right, class. Okay. Goodbye. Take care.
Thank you, ma'am.
Thank you, teacher.